class we discussed about the closed and open cycle gas turbine plant, and now we will be discussing the ideal thermodynamic cycle known as Brayton cycle, which simulates the processes in an open and closed cycle gas turbine plant. Let us see what are the closed and open cycle gas turbine plants which were discussed in the last class. Now, like this, if you remember, an open cycle gas turbine plant is like this. This is a turbine, as you know, so which takes air from the atmosphere, state 1, then at state 2 it compresses at a higher pressure and temperature, then it goes to a combustion chamber. This is not turbine, sorry, I am extremely sorry, this is a compressor which compresses the air to a higher pressure and temperature. Then the high pressure and temperature air goes to a combustion chamber where fuel is being injected and burned with the air, and a temperature is raised to a much higher value, this state 0.3, but remains at the same, the fluid or working system remains at the same pressure, 2 and 3 at almost the same pressure. Then it is being expanded in a turbine which gives the work, and this turbine and compressors are connected to a same shaft, so that they are being driven, the turbine is driven by the compressor. Then it comes out from the turbine at a state 4, which is at a lower pressure, but relatively higher temperature compared to 1, the lower temperature compared to 3. So, fresh air is again taken in. This was the open cycle gas turbine. In a closed cycle gas turbine, which was the concept like this, the compressor takes air as it is at 1 and it delivers air at a higher pressure and temperature, but difference is that instead of a combustion chamber, there is an heat exchanger where the heating of this air takes place by an external heat, that is, this is Q added, by an external heating source. That means, if a hot gas is there which is allowed to flow like this, which shares or exchanges heat, gives heat to the air, which comes here at 3, and then it is expanded in the turbine as usual to a relatively lower pressure and temperature, that is at 4, and these are the turbines and compressors as usual connected by the same shaft. So, difference is that now then again at 4, what happens, this high temperature air, but at the same pressure at 1 is being cooled by an external, this is the air flow, this is the cooled by an external source, that means here QE heat is rejected by an external source, that means the coolant is allowed to flow which takes the heat from the air. So, difference is that here during the process the fluid changes its composition, because here it is air, then when it is burned with fuel, so this part is the air and products of combustion, mixture of air and products of combustion, but here continuously the fluid is same fluid, that is air. So, each simulates a thermodynamic cycle because the working system remains the same. So, heat is being added here in this heat exchanger, which is the combustion chamber in an open cycle gas turbine. Here heat is rejected, that is the heat rejection, that is another heat exchanger, which is being simulated by the vast atmosphere of surroundings, which acts as a heat sink in case of an open cycle gas turbine. Now, we come to the ideal cycle for this power plant. So, these are known as Brayton. This cycle is known as Brayton or Joule cycle. Okay. Let us draw the cycle diagram in PV and TS plane. First PV plane let us do, or let us draw PV plane. Now, this 1-2 process, that is the process of compression in the compression, is ideally simulated by an isentropic process, S is equal to constant. Then 2 to 3, that is the constant pressure process where heat is added here at constant pressure process. So, 2 to 3 is a constant pressure process. Then 3 to 4 again in isentropic expansion, and 4 to 1 is, this is the direction, 4 to 1 is again the constant pressure heat rejection in a closed cycle gas turbine, it resembles. So, these are the ideal processes. So, this is a constant pressure process, this is a constant pressure process, and this constitutes a thermodynamic cycle in PV plane. Similar way, if we draw this on a TS plane, that is the temperature entropy plane, this looks like this. 1-2 is an isentropic process, 1-2, so 1-2. Now, this cycle you see operates on 2 limiting pressures, this pressure and this pressure, because pressure in this half remains constant sorry, the pressure in this hub remains constant. Here if you see that from 2 to 3, again from 4 to 1 pressure is constant, the two pressures. So compressor compresses from pressure 1 to 2 and the turbine reduces the pressure from 3 to 4. So better to draw, before drawing the the diagram, we should draw the pressure lines, constant pressure lines. These are constant pressure lines, then it will be easier. 1, 2 is the isentropic compression process, then 2 to 3 is the constant pressure heat addition process. So this state point 3. Then again 3 to 4, which is an isentropic process, will be a vertical line in a TS plane. So these are the directions, and 4 to 1 is the again the constant pressure process, heat rejection. These are the constant pressure process. So this is these are the diagrams in PV and TS plane. For the thermodynamic cycle, there is the ideal cycle for this power plant or the gas turbine plant, and this cycle is known as Brayton or Joule cycle. Now we will follow in the similar way the work and heat transfers in various processes. How to find out the work and heat transfer in various processes? Well, let me do like this. We place this thing like this. Okay, let me do. Now let us see that how we can make the similar way if we draw a diagram like this, or table, not diagram, a table like this. This is the process, then this is delta U, the way we did for earlier cases. This is W and this is Q, all right. And here one thing we always remember, that this is a steady flow process. So working fluid is air, so here I must write working fluid is air, and the process is a steady flow process, where I should write here a steady flow process. So this has to be remembered, steady flow process. So the equation, first law, dq is du plus pdv or du plus dw, will not be used in that sense, because it is a steady flow process, open system process. So let us first see process wise. 1 to 2 is an isentropic process. So therefore at the first instant Q will be 0, because there is no heat transfer. Now what will be the change in internal energy when we consider working fluid as air, which is an ideal gas? So change in internal energy is simply Cv times the T2 minus T1, all right. Now what will be the work transfer? Now work transfer, that is a steady flow process, the process in the compressor. Here the work transfer will be found out by applying the steady flow energy equation. And if we consider if the process is adiabatic, there is no heat transfer, because isentropic means reversible adiabatic process. So the work transfer is given by the change in the enthalpy. That means H2 minus H1, this is the work which is being done to the compressor. So H2 minus H1. So it is always positive, H2 is more than H1, and I have written taking care that it is done on the compressor. So therefore work is done here, W. Work is done here, W. But Q is 0 here. Q is 0 here. Q is 0 in 1-2 process. Now I come to 2-3 process. What is this process? This is a constant pressure process, but in a steady flow system. So steady flow system, constant pressure process means, just you see here, that means the steady flow where heat is added and the working fluid is increases, the working fluid is heated, or the temperature of the working fluid increases at a constant pressure. So there is no work interaction. So therefore in this process 2 to 3, work interaction is 0, all right. So what is the change in the internal energy? Internal energy change is Cv T3 minus T2, Cv T3 minus T2, all right. And we get the Q. What is Q? This is a heat exchange process, and the heat transfer is found out similarly by considering a steady flow energy equations around this heat exchanger, and we get the heat transfer is H3 minus H2, which is the heat added to the working system for the process from 2 to 3. Well, so therefore in the process heat is added and work transfer is 0 here. Work transfer is 0 here, all right. Now I come to the process 3-4, which is same as that of 1-2, where Q is 0. So 3-4, Q is 0, isentropic process. And change in internal energy always, since air is an ideal fluid, is always Cv, as you know, T4 minus T3, that the change in internal energy of an ideal gas is Cv into change in temperature. Now, here also the work done by the turbine can be found out by the application of steady flow energy equations as H3 minus H4. All right. Then comes the last process 4.1, which is same as that of 2.3, is a constant process heat rejection in the heat exchanger, in which case there is no work transfer. So, therefore, work transfer is 0. First I write that. Then the change in internal energy as usual for the ideal gas T1 minus T4, air is an ideal gas. And what is Q? Q is again by the application of the steady flow energy equation, we can write here H4 minus H1, which is positive and indicates, this is the scalar value which without any sign, that positive sign which indicates the heat which is being coming out from this system, well, which is being coming out from this system. So, in this case W is coming out. So, heat is coming out of this system, it is being H4 minus H1. All right. So, these are the work and heat interactions. Here also we can write the similar way, the Q is added, no work, no work. Here work is coming out, no heat transfer. Here the heat transfer, heat is coming out, but no work transfer, W is 0. Okay. Now, if you sum up the delta U, it will become 0, and if you make the algebraic sum of W and algebraic sum of Q, it will be is equal, but when you make the algebraic sum of W, you have to make one thing sure, that H2 minus H1 is negative, that means you will have to make a negative sign and then you will have to add. Similarly, in this case H4 minus H1 with a negative sign, then you will have to add, so that you can get an algebraic W is equal to algebraic Q. Okay. This is valid. Now, we come to the definition of thermal efficiency. How do you define thermal efficiency? That net work, that means work done on the system, work delivered by the system minus work done on the system divided by the heat added. And from the first law of thermodynamics, you know this can be written as Q rejected minus Q added. All right. And because W net is Q added minus Q rejected. Okay. Now, if you write this, then we will have to find out what is this Q rejected. Q rejected is H4 minus H1, H4 minus H1 is the Q rejected, this is the value of the rejection, heat rejection. So, minus sign is taken care of here, 1 minus as the definition of this is the scalar value, Q rejected minus Q added is H3 minus H2. So, this is the expression. Now, little more, if we want to expand this becomes like this. Well, you can see that H4. Now, this is again considering an ideal gas, we can write H4 minus H1 will be Cp T4 minus T1, well, divided by again Cp T3 minus T2. That means, I am replacing the enthalpy changes as the temperature changes, because for an ideal gas, change in enthalpy is Cp times change in temperature. If Cp is same, working fluid is same, and it considers an ideal gas where the Cp does not vary with the temperature. So, we get 1 eta is equal to 1 minus T4 minus T1 divided by T3 minus T2. All right. Now, with little mathematical exercises, we can show that this now we can express this in a different form. Now, if we consider this process 3-4, now this is an isentropic process, we can develop a relationship between temperature and pressure. I tell you that you will have to remember only for an isentropic process this equation, Pv to the power gamma is constant, where gamma is the ratio of specific heat. And other relationships like P and T and V and T in an isentropic process can be developed without remembering it by using the ideal gas equation of state, Pv is equal to RT, as you know. Now, here if you substitute V from this equation of state, you get RT by P whole to the power gamma is constant, from where we can tell T divided by p to the power gamma minus 1 by gamma is equal to constant. So, therefore, this gives the relation for T and P for an isentropic process, all right. Now, if we look on this 3-4 process, then we can write for the process 3-4 like this: T3 by T4, T3 by T4, okay. T3 by T4 is P3 by P4 to the power gamma minus 1 by gamma. Now, this P3 by P4 is defined as pressure ratio Rp to the power gamma minus 1 by gamma, where Rp is known as Rp, this is P, pressure ratio. Pressure ratio is very important parameter in a Brayton cycle, as the volume ratio is for an Otto cycle, because Otto cycle works on 2 limiting volumes, whereas the Brayton cycle as a gas turbine plant works on 2 pressure limits. There is one lower pressure and there is one higher pressure, that is from compressor inlet up to the turbine inlet. The fluid is at some pressure, constant pressure, this is the higher pressure or the maximum pressure of the cycle, and from the turbine outlet to compressor inlet is the lower pressure, all right. So, therefore, we define it as pressure ratio. In the similar way, one can define the T3 by T4 is this, one can define T2 by T1 for this process also. T2 by T1, considering this isentropic compression process, Rp to the power gamma minus 1 by gamma. So, now if we replace T3 in terms of T4 and T2 in terms of T1 here, we get eta is 1 minus 1 by Rp to the power gamma minus 1 by gamma. This is one of the very important relationships or expressions for the cycle efficiency of the Brayton cycle or thermal efficiency of the Brayton cycle in terms of the pressure ratio. It is similar to the expression of eta in terms of the volumetric compression ratio, where Rv to the power gamma minus 1, we deduced it in case of Otto cycle. Now, in case of a Brayton cycle, this is the expression. Now, you see the concept of regeneration. Now, I come to the concept of regeneration. What is that, the concept of regeneration? Okay, concept of, now I will talk about the concept of regeneration, regeneration in a gas turbine plant, concept of regeneration in Brayton cycle, concept of regeneration. What is that? Now, you see that if we look to the cycle diagram, we only draw the TS diagram now. If we look to the cycle diagram, TS diagram, we see the cycle diagram is like this: 1, 2, 3, 4, and this is the direction of the process. Now, in this cycle, the average temperature of heat addition, if we look from that angle of view, is some average between 3 to 2, and the average temperature of heat rejection is some average temperature between 4 to 1, which can be found out by dividing the enthalpy differences divided by the entropy change. So, we can find out the average temperatures. Now, if we look back to Carnot's theorem, you know that the efficiency of any reversible engine depends upon the average temperature of heat addition and average temperature of heat rejection. And also we know that efficiency of any reversible cycle can be expressed as 1 minus average temperature of heat rejection divided by average temperature of heat addition. And therefore, we can conclude from this, already we have discussed so many times this thing earlier, that if we increase the average temperature of heat addition, the thermal efficiency of a heat engine cycle increases. Similarly, if you decrease the average temperature of heat rejection, the thermal efficiency of a heat engine cycle increases. So, concept of regeneration does this. How? Now, if we increase the average temperature of heat addition in this way, that this is the air inlet at the compressor, state of air at the compressor inlet, before entering into the air inlet, before the combustion chamber or the heat exchanger in a closed gas turbine plant, if it is heated by this hot products which is coming out, or the hot fluid which is coming out from the turbine to a temperature of, say example here, some state point 5, by which this gas which exchanges heat comes down to a 0.6, then what we do? We make an internal use of the heat or the energy, thermal energy of 4 to heat this state to the state of fluid to the 0.5, we can increase the thermal efficiency. Let us understand this in this way. It is better let us consider a closed open system first. So, this is the compressor. So, this is the compressor, it takes at 1 and delivers it at 2. So, before going to the combustion chamber, it is being heated. It is being heated internally to the state 5. Then it goes to the combustion chamber where the fuel is used and the state point is 3, and then it is expanded in the turbine T. Well, expanded in the turbine T. So, what is done? This products of combustion and the air, that means this the working fluid at 4 is at a higher temperature. This is taken like this to heat it. That means this fluid heats the air. So, therefore, the temperature is reduced to 6 and then it is being rejected at 6, and again the fresh air is taken. The counterpart diagram for a closed cycle will be like this, where this part will remain same. That means the air is heated from state 2, this is the state 1, okay, to this point 5 by the incoming gas from the or incoming air from the turbine. Here only it is heated from external heat source, you understand, which raises the temperature to 3. Then it goes to the turbine. Well, they are connected by the same shaft, I must show. Then from the turbine, this hot gas 4 is going to heat this, and then it comes at this 6, where 6 is not rejected, in open cycle rejected and fresh air is taken. Rather, now this is being cooled, this is being cooled by the, here the Q is rejected by the external heat sink, and then this is going to the compressor, which means that the external heat is added only in the temperature range 3 to 5, that means to increase the temperature from 5 to 3. Similarly, heat is being rejected to decrease the temperature from 6 to 1, which makes that the average temperature of heat addition is now some average between 3 to 5 instead of 3 to 2 earlier, because air is already heated to 5 by the use of the internal energy. That means there is an internal heat transfer process. So, there is no external heat source. So, therefore, external heat source gives the heat to heat the fluid from 5 to 3, working system from 5 to 3. So, the average temperature is now between 3 to 5, which is more than the earlier one, which was between 3 to 2. Similarly, the average temperature of heat rejection is something between 6 to 1 instead of something between 4 to 1, which was the earlier case. So, therefore, we see the average temperature of heat addition is increased, average temperature of heat rejection is decreased. So, there is an increase in the thermal efficiency. Here, if we write the thermal efficiency expression, obviously the heat added, heat rejected, sorry, the numerator will be heat rejected, that is T6 minus T1, H1 divided by H heat added, H3 minus H5, which is equal to 1 minus, if you cancel the Cp, T6 minus T1 and T3 minus T5. And in this case, you will see that there will be an increase in efficiency. This is the concept of regeneration, by which we increase the temperature at the outlet of the compressor or the inlet air to some higher temperature by using the thermal energy. I will not tell heat, because heat is never contained in a fluid. So, thermal energy, or in loosely the heat content in this working fluid coming out from the turbine to heat this. Okay. So, this way the efficiency is increased, and this is the concept of regeneration in Brayton cycle. And this is this heat exchanger where air is heated with this fluid at 4, this heat exchanger, they are known as regenerator or regenerator, heated regenerator. They works in the principle of regenerative heat exchange. Well, now we will come to here also one thing before closing this. So, we can show it graphically in TS plane, that the heat given out away by this system which is denoted by this area must be equal to the heat taken by the fluid at 2, that means from 2 to 5 in the process 2 to 5. So, this area must be equal to this, though my diagram is not up to the scale. So, it does not show like that. Now, the Stirling cycle, we come to another important part, that is the Stirling cycle. Stirling cycle. What is a Stirling cycle? First of all, I tell you the specification. Stirling cycle working system is air, working system is air, and the process is non-flow process, Stirling cycle. Now, what we do in the similar way, we first draw the diagram of the Stirling cycles in PV and TS plane. So, this is the PV plane. So, in PV plane the Stirling cycle is like that. I just first draw the diagram, then I will explain to you. Well, these are the two isotherms and these are the two constant volume lines. So, these are the isotherms, T is equal to constant, and obviously these are V constants, a vertical line. So, let us start here from 1, 1, 2, 2, 3, 4, 1. So, in this direction. So, Stirling cycles consists of two isothermal lines and two constant volume lines. This is one isothermal line, this goes in this direction from 1 to 2, that means this is an isothermal expansion. This is a constant volume process from 2 to 3, okay, is a constant volume process from 2 to 3, and there is a change in the pressure, okay, and this is a isothermal process, constant temperature process where there is an increase in pressure, and this is again a constant volume process where there is an increase in pressure. So, these two process 3, 4, 4, 1 the pressure is increased, this is an isothermal process, this is a constant volume process, where process 1, 2 and 2, 3 the volume is decreased, a volume is increased, rather this process volume is increased and pressure is decreased, and this process volume remains constant but pressure is decreased. So, these four processes constitute the Stirling cycle. Now, if you draw the same cycle in TS diagram, 1, 2 definitely will be a horizontal line. Now, 2, 3 is the constant volume line, and the constant volume line gives a curve like this, a steep curve, which is V is equal to constant, and it comes at 3, where again 3, 4 is a constant temperature or isothermal process, and then 4, 1 is the constant volume process, V is equal to constant. So, therefore, the diagram is like that, that means the same diagram in the TS plane. This is the Stirling cycle. Now, working system air and non-flow process. Non-flow process means I can write that Q is equal to delta U plus W, which is very important. And as you know, earlier also used these things, and now we draw this table as usual. That means process, then delta U, then Q, and then W. WQ may be like this, earlier I wrote W here and Q, does not matter. Now, we start from process 1. Now, working system is air. So, air is an ideal gas, and we know delta U for an ideal gas is Cv delta T. So, when delta T remains constant, del U is 0. That means an isothermal process, internal energy remains constant for an ideal gas. So, you have to write this as 0. When del U is 0, so automatically you see if you put del U 0 here, Q becomes equal to W. So, Q and W will be the same, but we will have to find out the expression of any one of these. So, since it is a non-flow process, we can find out the expression of W from this equation. W is integral P dV, per unit mass basis I am doing. And for an isothermal process, equation of state tells that RT, P is RT by V and T is constant. So, that equation of state is PV RT, but for an isothermal process I can take T constant, so that it becomes dV by V. So, process is from 1 to 2, initial 1, final 2. So, this becomes is equal to RT ln V2 by V1. So, this is the W. So, for 1-2 process, W is RT ln V2 by V1. And you see, since Q is equal to W from first law, since delta U is 0 for an isothermal process where temperature remains constant, I can write Q as RT ln V2 by V1. Now, you see V2 is more than V1 from PV diagram. So, therefore, this is positive, this is positive. This is positive means what? The heat is being supplied, and this is positive means what? Work is being delivered. So, therefore, here the work quantity come out, that means work quantity come out, and heat is being supplied, and heat is being supplied. So, therefore, heat is being supplied. So, heat is being supplied because Q is positive. So, here in isothermal expansion work is being done and heat is being supplied. Then comes to the process 2-3. Now, here V is constant, 2-3 is V constant, and constant V in a closed system or non-flow process makes W 0 because PdV, integral PdV is W. So, constant volume process means work is 0. And when work is 0, immediately from this equation you get Q is equal to delta U. It is very simple, and delta U is as usual for an ideal gas is Cv into change in the temperature T3 minus T2, Cv T3 minus T2, and Q is equal to delta U since W is 0. So, Q will be also Cv T3 minus T2, all right. And here you see from the TS diagram T3 is less than T2, T3 is less than T2. So, therefore, W is negative, this is also negative, that means the internal energy is decreased, but I am now bothered, we are bothered more about W and Q. So, this is negative. So, negative W means what? Work, that means here you see that Q is, I am sorry, this will be Q, this will not be here. So, this will be Cv, yes, correct, T3 because delta U is Q minus T2, I am sorry. So, this will be. So, now you see W is 0, W is 0. Now, Q is negative, T3 is less than T2. So, therefore, negative Q means what? Heat is coming out from this system. So, heat is coming out from the system. So, in this case constant volume, the pressure is decreased. So, heat is coming out from the system. So, now we go to 3-4 process, again del U is 0. So, W gets the same value by integrating this PdV RT ln, the final volume is V4, this is V3, all right. Then what is Q? Q is now since delta U is 0, Q is W, so Q is also RT. Now, what is this T? I am writing RT, but this is 1, 2, so this will be RT1, RT1, T1, T2 is same, so you write RT1, RT1. Here I write RT3 because T3 and T4 is constant. So, RT3 ln V4 by V3. You understand this? That means I am finding out this W PdV for 3 to 4 process, again I repeat. So, we can write it as P is RT by V and T is T3 and T4 all same for the entire process. I can write either T3 or T4. So, I write RT3, that means it is not shown here. So, W is in this case RT3, similar way dV by V, and this process is for 3 to 4. So, that it gives this expression. That means, for any isothermal process, the work done in a closed system by a closed system in a non-flow process is R into T, that the constant temperature in the process, into ln final volume by initial volume. So, therefore, you see now V4 by V3, you see V4 is less than V3, that means this is negative, V4 is less than V3. So, this is negative. So, Q is negative, W is negative. W negative means work is being done, and Q negative means what? Q is coming out. So, in this process Q is coming out and work is being given. All right. Now, we are left with the process 4-1. What is this 4-1 process? 4-1 process is constant volume process. So, therefore, we can write the work done 0 in a non-flow process, and 4-1 process, the change in internal energy is CVT1 minus T4, and since work done is 0, the change in internal energy is Q. So, Q is CVT1 minus T4. Now, here you see T1 is higher than T4. So, therefore, both the quantities are positive. Now, Q positive means what? Here W is 0, first I write. Q positive means what? Q is being given. So, therefore, you see the process 4-1 receives heat, process 1-2 receives heat, while process 2-3 rejects heat, process 3-4 rejects heat. That means 3-4 rejects heat all right. Process 2 3 rejects heat, process 1 2 heat is given, and process 4 1 heat is given. And W quantities are 0 here for the two constant volume case. W quantities are 0, W quantities are 0. Here W work is coming out, here work is being given. So, by the arrows also in the cycle diagram we show the work and heat quantity interactions. Now, if we have to find out the expression for thermal efficiency for the Stirling cycles, we have to follow the same way, 1 minus. Now, if you sum up this, delta U is equal to 0. If you sum up delta Q is equal to delta W, showing the first law, validation of the first law of thermodynamics. So, 1 minus heat rejected by heat added, all right. So, that becomes equal to 1 minus where the heat is rejected. You see all these quantities are heat transfer. So, but we have to find out in which process 2, 3 and 3, 4 where they are negative. 2, 3 this is negative, and 3, 4, 2, 3 is the heat rejected, 2, 3 and 3, 4, and we have, sorry, this is 3, 4, oh sorry, this is 4, 1, I am sorry. So, heat is rejected where Q is rejected, this is the constant temperature process. So, heat is rejected here, heat is rejected here, that means 2, 3 and 3, 4. So, 2, 3 and 3, 4. So, 2, 3 is Cb T3 minus T2, it is negative, and 3, 4 RT3 ln V4 by V3, it is negative. Now, this negative value, since here is the negative sign, we will have to take in this way only their value Cb T2 minus T3, T2 minus T3, all right, okay, plus RT3, this is 3, 4 process, ln V4 minus V3, no, it is ln V3 by V4. Why? Because already negative sign I have taken here. So, only I want the magnitude of the heat rejection, ln it will be V3 by V4. You understand this? Then Q added, added is which one? Process 1 2 where Q is positive, V2 by V1, and so therefore I write RT1 ln V2 by V1, and another process where heat is being added is which one? 4 1, 4 1 where this is positive, Cv T1 minus T4. So, plus Cv T1 minus T4. So, this is the expression of the cycle efficiency for the Stirling cycle or thermal efficiency of the Stirling cycle. But the major concept of the Stirling cycle lies in the fact that we conceive of heating this part, this constant volume part. Let us see the TS diagram, that heating of this working system during this constant volume, here heat is added and here heat is rejected. So, this heat is being utilized to heat this part. That means there is a concept of regeneration. That means if we think of a regeneration where this heat, that means this area, that is the heat which is rejected by the process 2 3 is utilized to heat the working system in the process 4 1. That means if we can make these two area equal, so that this utilizing the same heat is a concept of an ideal regeneration, that if we reject the heat from state 2 to 1 by the process, and if that heat is taken by the working system during the process 4 1 and reach the same temperature 1, that is that of the 2, that means is inlet temperature, and also this while rejecting heat reaches the same temperature, that is 3, as that of its inlet at 4, then what happens? These two processes act in a sense that the heat transfer between the two processes are taking place internally. That means we are using the energy of the fluid, working fluid within the cycle. So, only heat transfer from outside is in this isothermal process 1 2 and the isothermal process 3 4, while heat is added in the isothermal process 1 2 and heat is rejected in the isothermal process 3 4. Therefore, it becomes almost a Carnot cycle, almost, not exactly a Carnot cycle, not almost, and therefore, here we see that in that case we eliminate the heat rejected here in the process 1 4, which term we will reject? Then we will reject this term. That means the process 2 to 3, that means when we get the heat rejection Cb 2 to 3 and 3 to 4, that means this one will neglect, because heat is rejected only in the process 3 to 4, that means in isothermal process. Similarly, in the heat addition process, this part we will neglect when you write the efficiency part, that means T1 minus T4. That means this is the heat added, heat rejected at constant temperature, this is the heat added at constant temperature, because they are internally. That means this heat addition takes here to, this heat rejection is taking here, taken by the fluid to make this addition of heat. So, therefore, these two things will be cancelled. So, only heat addition is this term which is rejection, sorry, is this term which is there at this constant temperature, only heat addition is this term which is there at constant temperature. And if we see that, you see that since V1 is V4 and V2 is V3, we can write that V3 by V4 equals to V2 by V1. Obviously, because there the V2 is V3 and V1 is V4. So, therefore, V3 by V4 is V2 by V1. So, therefore, R and R cancels. So, eta becomes equal to 1 minus T3 by T1, which means that the efficiency equals to the 1 minus temperature, the maximum temperature of the cycle divided by the minimum temperature of the cycle, that is the Carnot's efficiency. This is Carnot's efficiency. So, therefore, we see by a concept of complete regeneration in a Stirling cycle, in this way we will give rise to a thermal efficiency equivalent to the Carnot cycle. That means, this cycle will work as a Carnot cycle provided there is an ideal regeneration. That means, we can take the entire heat rejected in this process to heat the working system in this process, so that this temperature equals to this temperature. After getting the heat, its temperature will be equal to the initial temperature of this working system while rejecting it, and these two temperatures are equal. So, that these two process heat transfer does not come into the calculation of the cycle, because only external heat addition at this temperature, that is isothermal heat addition and isothermal heat rejection, as it happens in Carnot cycle. Okay. Again, now we will discuss another cycle known as Ericsson cycle. It is similar to Ericsson cycle. It is almost similar to a Stirling cycle, concept is almost same, but difference is that your working system is there, these are all same, and non-flow process, but the only difference, non-flow process, but only difference is that the cycle, that means the processes in the cycle. In the Ericsson cycle, the PV and TS diagram if you draw, then you will see that the same isotherms are there, but we have constant pressure process in between. That means, this is the concept, that 1, 2, this is the cycle 3, 4. That means, this is the Ericsson cycle. So, Ericsson cycle comprises 2 isothermal processes and 2 constant pressure process. So, this is an isothermal expansion, this is a constant pressure process where volume is reduced, this is again an isothermal compression process, and this is again an isothermal constant pressure process where volume is increased. Similarly, if you draw this thing in TS diagram, you will get this 1, 2 process, this is 1, 2, and then 2, 3 is the constant pressure process. Constant pressure process you saw is a relatively flat curve compared to the constant volume process, 2, 3, then again 1, 2, 2, 3, 3, 4, 3, 4, 4, 1. That means, 1, 2 is this process, isothermal process, 2, 3 constant pressure process, T is equal to constant, 3, 4 again is isothermal process, T is equal to constant, and 4, 1 is again the constant pressure process. All right. So, this comprises the Ericsson cycle. Difference is that in Stirling cycle, there were 2 constant volume processes instead of 2 constant pressure processes in between the 2 isothermal processes. Now, again if we write in the similar way that the first law of thermodynamics Q is del U plus W. Now, I go on writing the same way, process, then delta U, then Q, and then W. All right. Now I do like this. Again the process 1 2 remains the same as usual. For process 1 2, delta U 0 isothermal process as we did earlier. So W is evaluated as PdV as we did earlier. So R T1 and T2 are same. So this is ln V2 by V1 and Q will be R T1 ln V2 by V1, all right, and V2 is more than V1. So both Q and W is positive. So therefore there is a W coming out and there is a Q going in by the nomenclature. So for 1 2 there is a W coming in, that work is done, and there is a Q going in, W coming out and Q going in. So similarly the 2-3 process, but 2-3 process earlier this process was a constant volume process, there is a constant pressure process. Now in constant pressure process, first of all there is a change in the temperature between 2 and 3, and therefore we have the internal energy change is Cv T3 minus T2, because it is an ideal gas, change in internal energy is Cv into change in the temperature. Now Q and W both quantity are there. Now here at the constant pressure process in a non-flow system, how do you find out the work? Work is PdV, and the constant pressure process P into delta V, that means the change in volume. So therefore it will be P2 into change in the volume V3 minus V2. So all right, V3 minus V2. So this is the Q. Now W, sorry, I am sorry, this is the W, I am sorry. Now Q will be found out by either adding these two, same thing will be will result that if we add these two, this will be nothing but H3 minus H2, and also by applying this concept we know in a non-flow process at constant pressure the heat added is equal to the change in enthalpy, that means final enthalpy minus initial. If we add these two things, P2 V3 minus P2 V2, and you see the P2 is constant, so P2 is P3 also, the P3 V3 minus P2 V2. So if you add that, then it will be H3 minus H2. Okay, all right. So otherwise we can write simply H3 minus H2, because this is a constant pressure process between 2 to 3. So at constant pressure process heat addition is the difference of enthalpy. Now you see that V3 minus V2, V3 is less than V2, so this is negative. So work is negative, means work is done. So work is done on this process. So in 2-3, in the 2-3 process, so this is 1-2, this is 2-3, 1-2 is there. So 2-3, you see the work is V3, P2 V3 minus V2. So therefore work is done on this process, 2-3. All right, okay. So work is done on the process. Then Q, what is Q? H3 minus H2, and H3 minus H2, it is nothing but the difference in temperature into Cp, specific heat at constant pressure, because air is an ideal gas. So T3 is less than T2, so this is negative. That means heat is negative, means what? Heat is coming out of this system. Heat is coming out of this system, H3 minus H2. So heat is coming out of the system. So all right. Now this is again an isothermal process, 3-4. 3-4 is again an isothermal process. What happens to 3-4? The same thing, delta U is 0. This is RT3 ln V4 by V3. That means this is the work done, RT3 ln V4 by V3, and since delta U is 0, Q is W. So Q is equal to RT3 ln V4 by V3. All right. Here you see V4 by V3. So V4 is less than V3. So therefore this is negative, this is negative, which means V4 by V3, you see V4 is less than V3. So this is negative, that means work is being done on this system, and V4 by V3 negative means heat is being also coming out from this system. So in these two process 2, 3, 3, 4, we see work is being done and heat is being coming out. Now we see the process 4-1. 4-1 again is a constant pressure process, like 2-3 process. So here the change in internal energy is Cv times the T4 minus T3 as usual, T4 4-1 T1 minus T4, T1 minus T4. Now the Q is T1 minus T4. Now, similarly, we can write P, W is the similar way P1, here we can write P4 or P1 into V1 minus V4, V1 minus V4, all right, and this one will be again H1 minus H4, changing the enthalpy. Here if you see the sign, we see V1 is more than V4, so therefore here work quantity is positive, that means work is coming out. I am showing here, it can be shown here also, work is coming out, and heat quantity H1 minus H4. What is H1? H1 is higher than H4, all right. So therefore heat is being supplied here. So you can draw it here, 1, 2, work is coming out, heat is going in, 2, 4, 1, sorry, it is not 1, 2, 1, 2 is all right, 4, 1, work is coming out, heat is going in, all right. For 1, 2 it is there, for 2, 3 work is going in and heat is being coming out, okay, and for 3, 4 work is given in and heat is coming out. So now we can find out in the similar way eta as 1 minus heat rejected by heat added, all right. Where are the heat rejections? You see V2 by V1, these two process 1, 2, and now the heat rejection is 3, 4 and 4, 1, 3, 4 and 4, 1. So 3, 4 process, this is R T3. Now I write the ln V3 by V4, the values, not the negative sign, V4 by V3 already negative sign is taken, and 4, 1 is H1 minus H4, that is Cp T1 minus T4, but I write T4 minus T1. Sorry, I am sorry, this is written T1 minus T4. This is the process, sorry, this is the process 4, 1. So therefore process 4, 1 heat is being supplied, not heat is rejected. Heat is rejected in the process 2, 3. So it will be Cp T2 minus T3. That means Cp T2 minus T3. That means this one. This one I take T2 minus T3 positive value. Okay, divided by the heat added. Where the heat is added? Heat added, we have to find out the processes where heat is being added. Heat is being added in the process of 1, 2. 1, 2 is an isothermal process where heat is added, RT1 ln V2 by V1, plus one is another process where heat is being added apart from this isothermal process where heat is added in this 4-1 process. Heat is added in the 4-1 process. So therefore plus what is 4-1? 4-1 process is H1 minus H4, Cp T1 minus T4. If you do it carefully, it will come. Now again, if we consider a regeneration concept in the similar way, that means heating in the process of 4-1, heat added in this process of 4-1 can be made by cooling the working system in the process 2-3. That means if we use the heat rejection in the process 2-3 to heat the working system in the process 4-1 completely, so that by taking this heat the working system changes its temperature from 4 to 1, which is the initial temperature of this fluid rejecting heat, and its final temperature equals to this initial temperature, which means a complete regeneration, ideal regeneration, the entire heat transfer for the process 2-3 is used to make the process 4-1. Then only addition of heat is that 1-2 process and rejection of heat at 4-3 process. That means heat is added and rejected only at the constant maximum temperature and minimum temperatures of the cycle, and that makes the cycle a Carnot cycle, and therefore eta becomes equal to 1 minus, in that case this part will be 0, this part will be 0. Again we cancel R and we can find out 1 minus T3 by T1, but here you have to change this V3 by V4 before doing so V2 by V1 in terms of the pressure ratio, otherwise it will be not possible for you to prove. So that you have to find out this in terms of the pressure ratio, that means you reuse the PV to the power gamma is constant, so that you can find out the V3 by V4 is P4 by P3 to the power 1 by gamma, then V2 by V1 is P1 by P2. Now P1 by P2 is P4 by P3, okay, all right, because P3 V3 to the power gamma. In 3-4 process is P4 V4 to the power gamma, and again P1 V1 to the power gamma is P2 V2 to the power gamma. So, we can change the ratio. V3 by V4 is P4 by P1 to the power 1 by gamma, and V2 by V1 is P1 by P2 to the power 1 by gamma, and P1 by P2 is P4 by P3. All right. So, that we can substitute this and we can see that this terms cancels out. So, ultimately eta is 1 minus T3. Therefore, we see that the concept of Stirling and Erikson cycle with complete regenerations works as a Carnot cycle. In a Stirling cycle, there are 2 isothermal processes and 2 constant volume processes, and in an Erikson cycle there are 2 isothermal processes and 2 constant pressure processes. And if we can have a complete regeneration, that means in a Stirling cycle the heat transfer in the 2 constant volume processes are made in such a way that heating process, the heat is taken from the cooling process, and similarly in case of Erikson cycle the 2 constant pressure processes where heat is coming out in one process, heat is going in other process, and we can make a complete regeneration between this heat transfer. Then only heat addition and rejection takes place at the constant temperatures isothermal processes. That is the maximum temperature of the cycle heat is added and the minimum temperature of the cycle heat is rejected, and the efficiency becomes equal to the Carnot cycle. So, therefore, here I end the discussions on gas power cycles, that is the ideal air standard cycles which simulates the gas power plant, or which are the theoretical cycles of gas power plant. We have discussed Otto cycles, we have discussed diesel cycles, we have discussed Brayton cycles, and finally Stirling and Erikson cycles are the concepts, so that with an ideal regeneration how we can conceive of a process which targets to an efficiency equals to that of Carnot's efficiency. Thank you.